terms of things we're doing today, we are wrapping up just a couple closing ideas about translational motion. So the problem we've been working on, the free particle, the particle in a box, they've both been about translational motion, about just things moving around. And if we want to understand atoms and molecules, we need to understand three different types of motion. We need to understand translational motion. That's what we've been working on. Then we need to understand vibrational motion. That's going to be the next thing we do, thinking about, you can imagine bonds as these attractive forces that act like little springs and act like vibrational motion. And then we need to understand rotational motion, molecules spinning around in space, or electrons kind of trapped in a rotational space around a nucleus. So we'll get to all of those. The things that we are going to talk about today have an order I want to do them in. We'll see if I stick to that order. We're going to talk more about the uncertainty principle. That's what we've got from last time up here, talking about how the variance of these two different measurements we could make relate. Did I do something wrong?
Are they flipped?
They may be. I had a typo in my notes. Let me think about this. As the box gets, box gets smaller. Yeah, they're flipped. Sorry about that. In my notes, I had them written completely. I had them written with the completely wrong subscripts in my notes. Yeah. No. Okay, that's better. Thank you for catching that. The other thing we have to do is talk about the uncertainty principle, this idea of variance and how it multiplies together to give this idea of uncertainty and what kind of minimums we can talk about. Then we're going to also talk about translational motion in multidimensional space. So rather than just doing everything in 1D, what if we wanted to talk about a particle in a plane or a particle in a cube? And how would we talk about those different ideas, taking this one-dimensional idea and expanding into multi-dimensions? Turns out it's not that bad. And then we're also going to talk about something that I think is pretty interesting. It's the purely quantum phenomena of tunneling. And each of these things are going to lead to us talking about something that's going to be useful later in the quarter. So that's part of why we're doing these three things. All of them are going to be things that are useful later in the quarter as well. Questions so far? Okay, thank you for catching that. So the big thing we're asking when we're looking at this idea of commutation, we're looking at, does the order of operation matter? Does the order of operation matter? We're trying to figure out, is this 0? Right? And it turns out that that question leads to a somewhat fundamental idea as to how well we can know two measurements simultaneously. I've been thinking about the whole error bars thing, and it's not exactly just error bars, because error bars exist when we know trying to know these two things. But theoretically, if this commutation was 0, we could know both perfectly. So the uncertainty that we are observing is not just from the uncertainty of measurements in general, it's the uncertainty of these two measurements together at the same time, kind of denoted by the commutation. We can show this. There's another way we can think about it. We can do kind of two examples. An example of some place where we don't have uncertainty. We can imagine, do the commutation of the Hamiltonian operator for a particle in a box and the momentum operator. Is that 0 on a function? Right, we can write down the commutation, we can write down the commutation operator, what this would look like. It's almost always a better idea to do it with some test function. We'll do it for a test function with variable x. We can say, is this going to be a 0 value or is it going to be a non-zero value? Talk to your neighbor. Can you tell real quick just by glancing at it? I'll start to rewrite it, but talk to your neighbor, see if you can figure it out. Talk. Start with writing down the Hamiltonian.
Like the bottom one.
Oh, you think it's not?
And so,
I think it can't be 0. There's no way.
yeah. There are way too many symbols.
No way.
What do you think?
No, because 0.
Thumbs up for yes, it's going to be 0. Let's do thumbs up if it's going to be something besides 0, thumbs down if it's going to be 0, because 0 is a lower thing than not 0. Thumbs up if it's 0, thumbs up if it's non-zero, thumbs down if it's 0. Ooh, kind of split. Sideways if you think it's a trick. It turns out, okay, so it turns out when we start rewriting this, this ends up being 0. Right? And it happens because when we think about the Hamiltonian operator, it's kinetic energy when we're just doing particle in a box. There's no potential part. So it's momentum squared and momentum. So when I start trying to FOIL this out, when I plug in all the definitions, this is going to be like a 1 over 2m px squared hat px hat on psi minus px hat px squared. I think I forgot a negative, right? No, because the negative comes from that. Okay, I'm okay. Px squared hat on psi. Now, the px is a negative I h bar d by dx. So this would be like, I'm going to have essentially the main part, the main function. We've got some constants there, but this is like taking the derivative. Does the order of taking the derivatives, this is just going to be, right? Since it's the same mathematical operation each time, it turns out what we're going to do is take the third derivative of that function minus taking the third derivative of that function. We're doing the exact same mathematical operation in this case. This ends up being 0. So in this situation, there's no uncertainty between the Hamiltonian, our energy operator, and our linear momentum operator. So we can measure both of those at the same time and know exactly what they are without any uncertainty. Not the case for position and momentum. So we can look for situations where it's like, oh, is this actually going to have some uncertainty to it or not? And without getting into the math of how this gets derived generically, there is a generic equation for this. For the uncertainty of two operators, we look at the variance of operator A with the variance of operator B, and it's greater than or equal to negative 1/4 integral, make sure I don't get this wrong, right? We do the integral with a particular operator. We do the commutation operator of A with B. We essentially ask ourselves, oh, I forgot one more thing. Square. We essentially ask ourselves, does the order of operation matter? Do these two variables relate to each other in some fundamental way? That makes it so the order in which we work with them makes a difference. And that's just what this commutation in the middle is doing. A commutator operator really just creates a new operator that's operating on that function. That's made from these two operators being put together in different ways. Question?
I know it necessarily doesn't matter because it goes to 0, but on the Hamiltonian momentum one, does the 1 over 2m apply to both values or just to the first one?
It would apply to both values because it's on this one and it's on that one.
Oh, okay, yeah.
Right? Because it's in the way it foils out, it's going to be applied to that one and to that one, so I just pulled it out. Same thing happens with the negative IH bar. It turns out we're going to have a negative IH bar 1, 2, 3 times for both, and I can factor that out as well, and just look at the fact that it ends up being d cubed, dx cubed. Question?
Why would the order affect, like, if it goes to 0 or not? Who's confused on that?
That's the kind of weird part of it, right? So in this one, the order doesn't matter because these operators, the order of operation doesn't matter here. We saw last time, if we looked at this one, and I can rewrite this one real quick if we don't remember this from last time. This one, the x hat operator is multiplied by x, and then we've got our negative IH bar d by dx. right? And we can apply that to psi, and we're taking the derivative of psi. If we do it in the other order, where I've got my, do it like this, I've got my negative I h bar d by dx, and now I'm applying that to x psi. Here I have to apply the chain rule. If I multiply by x before I take the derivative, I get something different. That's weird. That should be weird to all of you. I don't know about you, but the first time when I first took an intro to quantum mechanics class like this, that was the first time I saw non-commuting mathematics. Right? This idea of mathematics not commuting, I didn't see that until I got to this class, to something like this class. And so we actually have the order in which we do the operations matters. And part of that comes from the fact that the mathematical operations we're doing are more complicated than we typically see in a math class, right? We're using applied taking the derivative as a mathematical operation we're doing. And if you multiply by x or x squared before you take the derivative, that's going to be different than taking the derivative and then multiplying by x. Another version of operators that would commute, if we did like position squared in position, where it's just multiply by x, that's back to our normal multiplication stuff, and that's what we're used to, and that commutes, and so that ends up being 0. So that lets us know we can do the uncertainty and the position at the same time, because those two things would commute. But these two don't. And these things that don't commute, they have a special name. It's a whole mathematical theory. This ends up being a Fourier pair. Same person who did Fourier transforms. It's a mathematician. And again, these relate to each other because they're fundamentally related to each other. Position and momentum. Momentum is defined as the change of position. Position is the position. They're like fundamentally connected to each other. The reason we don't see that same problem with the energy is momentum squared and momentum. Energy is just momentum squared, so you need to know the momentum to do the energy anyway. So you kind of have that direct relation where it's really just doing the same thing, and you have this kind of more complicated relationship. Question?
Is that notation where you see the brackets in the two operators and the function, where it foils out to be first one, then the other? Is that like standard?
Yes.
Okay.
So this notation is really standard for commutation operators. So if we wanted to look at this generic one, if we wanted to look at a hat comma b hat, operating on some functions, that would be essentially defined by first one, second one on function, minus second one, whoa, getting carried away, first one on function. That is by definition. And the order really, really matters here. Right? If you look at this, if I did BA, would that be the same thing? No. What is it if I do BA? Do me a favor, calculate real quick, calculate what BA would be. Right? If we flipped our order in the commutation, and we did B hat, A hat, what's that equal to? With the test function, What's that going to be equal to? Awkward table drag. No, this way. Assume you can do the easy part. Can you do the easy part? Right. Probably did the easy part in your head. Let's just BA on psi minus AB on psi. Operators for all of those. Great, right? Easy. But do you see the bigger part of this? Do you see the bigger pattern? AB to BA, these two relate to each other. How is this one same or different from this one? What's it off by?
Negative.
Turns out the order of operation can be related to each other. Through this idea of just writing it out, noticing it's different by a negative sign. This will be handy. So when we start doing, you notice one of the types of motions I mentioned we still have to do is rotational motion. And when we start talking about angular momentum, these commutator operators are actually going to be really useful, because the way that the x component of the angular momentum and the y component of angular momentum relate to each other is going to be through commutation operators. And at first, it's going to look really complicated. There's like a worksheet, like the math one I gave you last time, where you have to do all these things, and you're like, this is insane. And then it's just like, oh, one rotates into the other. It looks like the right-hand rule. And it turns out that it's really, there's a lot of math to get to that, but it just ends up being the right-hand rule, like x cross y gives you z. Or negative z, I can't remember which one. Oh. No, it gives you z. Okay. Right, but it turns out that there's going to be a relation like that we're going to be able to prove through this idea of commutation. Everyone's doing that. Is that right? So, Heisenberg's uncertainty principle doesn't mean that all measurements have uncertainty in them. We kind of get the idea of all measurements have uncertainty in them because we're dealing with wave particles that have spread to them, rather than dealing with finite particles. But in terms of making measurements, Heisenberg's uncertainty principle says it's actually a property of the two observations we're trying to make. Is it position and momentum? Is it energy and momentum? Is it position in like another position? Right? Measuring the x position and the y position, those things are going to commute. Multiply by x, multiply by y, that order isn't going to change. Question?
Does the uncertainty principle work for all non-commutable operators?
Yes. Right, so this is a property of all non-commutable operators. Anytime we have two operators that don't commute, there's some amount of minimum uncertainty associated with that. And it is a minimum uncertainty. Again, if you remember last time, some people laughed at this. You can always make really bad measurements. Right? When we look at this uncertainty here, this sigma x squared, sigma px squared, it has a value. It has a minimum at a really small n, and it blows up to infinity as n gets really large. That's your minimum, not your maximum. So your maximum can always be like giant. Okay, so let's see here. Okay, now, one of the things I just mentioned is that x position and y position commute. However, we've never done anything with y position. Should we see what happens if we try to do a particle in a plane rather than a particle in a box?
Yeah, let's do it.
Okay. So this is not going to be as bad as you might think. We're essentially doubling the problem. So everything we did twice as much. But same answers, just on a different axis. Now, to do this, we're going to have to do something pretty interesting that we're going to do over and over and over again. It's one of the tricks we saw from our classical physics on the first day. We're going to have some function. I'm going to use a fancy psi with like arms on it to make it look different from our usual. And this function is going to depend on position x and position y. And I'm going to say, I bet I can do this as an x portion and a y portion. If I have a vector that's pointing along in some diagonal direction, I can look at the x component and I can look at the y component for a classical analogy. So I'm going to go ahead and I'm going to think about this in terms of an x component and a y component. And again, just to make these look different than letters, I'm going to put fancy arms on them to just make them so we don't confuse them with just the variable x. This is some function on the x-axis that only depends on x. This is some function on the y-axis that only depends on y. Similarly, I can take the Hamiltonian and I can write an xy Hamiltonian. Again, we'll do it in two steps, where I can look at, now that I'm thinking about it in terms of the two variables, I can think about it in terms of, well, I'm going to have the momentum along the x-axis, and I'm going to have the momentum along the y-axis, and I'm going to have some potential that could depend on both x and y. If we're sticking with particle in a box, the same thing we've been doing. That piece goes to 0. That piece goes away when we're looking at particle in a box, and we just say, look, I've got this momentum, I've got this momentum. Then we do a little trick. Okay, this is the important trick. We do two things. First off, we're going to have our xy, our two-dimensional Hamiltonian, operating on our two-dimensional wave function, giving us a constant energy and that two-dimensional wave function back. Right? Still have the same normal Schrodinger equation we have. It's just now there's extra dimensions inside of it, but it still looks pretty much the same. We could even do it for 3 dimensions. We'll do that at the end. The trick that we use is we say, look, this is a constant. Right? That's just some energy constant. And we can say, where's my bit? Oh, there it is. Okay. We can say a constant can be made up of 2 different constants. So I can say, hey, my constant energy, that's made up from a constant 1 plus a constant 2. Or, if I wanted to, instead of calling it 1 and 2, I can say it's a constant in the x direction and a constant in the y direction. You know, 5 can be 2 plus 3 or 1 plus 4. It can just be other numbers added together. So we essentially get to say, look, this energy, that's the constant for the two-dimensional problem, we can say it's equal to some energy along some energy x part and some energy y part. This is going to allow us to start to separate out the problem. Now we're going to plug all this in together and do some rearrangement. Am I ready for that? I'm trying to decide how many steps to skip. I think none. So I don't have them all written down, but here let's just do it bit by bit. So we're going to have px hat squared over 2m plus py hat squared over 2m on xy is equal to ex plus ey functions xy. Okay? Then we start rearranging things. If this is derivative with respect to x, it does nothing to the y part. So I can bring this around and I can say, look, if I've got derivative with respect to x on this xy, that would be that y part, there's nothing to take the derivative of in the y part. That y part doesn't depend on x at all. So this ends up letting us pull the y part out and then having px just operate on the x part. Same thing is true for the y part. So when I do the py, the x part can kind of just sneak through. So I rearrange, enough that I kind of change colors. So I'm going to have y px hat x squared divided by 2m plus x py squared hat on y divided by 2m is equal to ex plus ey x function, y function. Now, I divide this over, when I divide this function over, the x over here, I'm going to do that real quick, so I'm going to divide this over in this same line. Don't get mad at me. I divide that xy over. right? And then notice, my x out front here cancels with the x down there. It's hard to write a line through x. Right on top of it. My y part up here cancels with the y part down there. So I end up with this chunk a chunk that only depends on x and a chunk that only depends on y. And I say, hey, those two things are going to add up to a constant, so I'm going to set them equal to their own constants because two constants just add up to a constant. Now this separation of the constants into one constant, means that these two equations are still connected to each other through this combination of energies. But it does allow me to split them up and solve them separately and say at the end I have to add them back together. Question?
I was wondering why don't you just go and cancel out the big X, big Y in the first step?
I could have.
Yeah,
I
just
could.
like- 'cause
Oh, because the application of the operators, right? We should apply the operators. The only thing that allowed us to do this was the fact that py didn't operate on x, so we could move it out. We have to be really careful about operators when we're in quantum mechanics because of this idea of like, do they commute or not? So we had to FOIL it out, and it was essentially this step that was necessary in order to cancel them out. Right? Showing that one of them didn't get operated on. Generically, this might not be true, but for these operators, because of this step, we get to do that cancellation. Another question. Okay. So, I'm going to look at the x part first, because it's going to look really familiar. And I'm going to rearrange a little bit more as I do this. Right, I bring that lower x back over to the side. I say, look, it's just equal to ex. I bring my function back over. And we're back to the one-dimensional Schrodinger equation along the x-axis. And we know how to solve this. We know the answers to this. Right, we're going to end up with x functions. They're going to be 1 over square root of 2L sine n pi over L in the x direction. X. Right, so now we've got a box that's going to have some length in the x direction and some length in the y direction. But we've solved this before, and we can get the energies associated with x because we've solved this already. Those energies end up being n squared, I squared, h bar squared, over 2ml in the x direction squared. Right, and we could spend 20, 30 minutes going through this calculation again and solving for the, but we've done this already, right? This is just the same problem we did for particle in a box. The one catch is, we're doing this for a second thing. I'm actually going to label my n values as the n values associated with x. I'm just going to call them n1s for the n values associated with x, and then n2s for the n values associated with y. Guess what the y part does? Same thing. Same thing. So over here, we got our only y part. We end up with a 1 over 2m. Py hat squared, that's a weird hat, on the function y, it's going to be equal to that y energy with that function y returned. I'm going to do it in a different color just for fun. Our y functions, oh, I forgot a subscript over here. This is root 2Lx. Don't forget your sub. Every length we need to know we're talking about the length in the x direction or length in the y direction. 2Ly sine n pi over Ly, and our EY is equal to N2 squared, pi squared, h bar squared over 2mly squared. Two different parts, right? So it turns out that because we can do this separation of variables, because this operator, the way we conceptualized how we're going to break it up in these orthogonal vectors, and the way we formulated our Hamiltonian in terms of x momentum and y momentum, we're able to split out, do this separation of variables for the x part and the y part, saying that they're going to add up these two constants, this Ex constant and this Ey constant, add up to the total energy constant. This is something we're going to do when we look at anything in multi-dimensions. Anything with multiple dimensions, we're really often going to do separation of variables, and we get all kinds of weird restrictions because of it. Do you remember the rules for M sub L? Oh, wow, that's like a 124 thing. Like, okay, do you remember 1s, 2s, 2p?
Oh, yeah.
Right? Do you know why that you don't have like a 1p? Because of separation of variables and the way that the different pieces equal. We're going to derive that this quarter. We're getting there. We're actually going to derive all that stuff and come up with why we use the different functions, the different shortcuts we use from solving multidimensional Hamiltonians. We're going to get there. But this is our first kind of looking at something multidimensional, and there's some interesting consequences here. Right? I'm going to erase this bit here, and we're going to look at what the total energy and what the total wave function is. We're going to look at what this psi, this big psi is, and what this E total is, just by multiplying these together and adding these together. Ready for that? Okay. So for this two-dimensional particle in a box, our wave function becomes those two things multiplied by each other. So our wave function ends up being equal to square root of 4 over Lx Ly, right? I'm just multiplying that together. Sine n1 pi over Lx. Sine n2 pi y. That's going to be our xy wave function. It's just two sine functions multiplied to each other. Okay, no, I got my subscripts in there. Two sine functions multiplied by each other, but going in different dimensions. And this creates some really cool pictures. My favorite's not in the textbook we have, but in a textbook, the textbook that I had back when I was at UC Riverside. Again, flyers if you're interested. I don't think this one has a picture like this, but it's really cool. It's got these nice kind of like dimensional map pictures of how you would look at them. So you end up with functions that kind of look like this, where you got positive and negatives. You got waves that are kind of moving in and out of a plane. The one that I really like is there's a picture of like a drum head at different because that's a vibe. But instead of we've been doing strings, if we wanted to do something that was two-dimensional, it's like a drum. And you can actually look at the different standing waves that you create on a drum when you're hitting on it and get the different sounds out of different drums from the XY dimensions of it and how hard you hit it. And you get the same kind of idea, like you can get two-dimensional standing waves, and it's really cool looking. The other thing that happens that's really interesting, becomes interesting in multiple places, is we've got this total energy, which is going to be these two things added together. So notice most of this is constants. Pi squared h bar squared 2m, that's all constants. I'll pull that out. Pi squared h bar squared over 2m. We're left on the inside with n1 squared over Lx squared plus n2 squared over Ly squared. And there's something funny that happens here, is I could have n1 equals 1 and n2 equals 1. Oh, question?
Could you just quickly restate what the big psi represents
So-
That's a function, but could you be more?
So this big psi is the two-dimensional function, right? It's my x part and my y part multiplied together. So I'm taking this x part, multiplying it by this y part to get the overall like two-dimensional wave function.
So could it be like representing either position or momentum?
No,
Like
it is the wave function in 2 dimensions. So now we could go and ask questions about, well, what can we say about the x position? What can we say about the y position with this two-dimensional function? Do those two things relate to each other? Are they separate from each other? If we look at the commutation, x and y measurements are separate from each other, but we have to start asking questions about this. So this is just the setup, and now we can ask, what's the position? What's the momentum? What's the variance of the x position? What's the variance of the y position? What's the momentum in the x direction? What's the momentum in the y direction? Right? This is just the wave function
I see.
that now we can do all of those questions about. Question back there, then up here.
Okay, I have two.
Yeah.
So going back to that equation we bracketed with the star,
Mm-hmm.
did you say that you multiplied that through?
Yeah, so it turns out when we look at the px operator, as a reminder, I'll do it here. When we look at the px operator, that's negative I h bar d by dx. It's just take the derivative with respect to x. Because of the way we defined the y part, was the derivative of x, if you take the derivative of a y function with respect to x, it does nothing. It just comes through. Right? So when I try to take the derivative with respect to x, the y part it does nothing to, but the x part I still need to operate on.
What happened to the 2m?
The 2m, I bring that back in over here. I was just looking at the operation step.
Oh,
Right? So if you look down on this line, the 2m is still there. This was just me considering the operator portion on the functions. That constant is still there, and I bring it back in down here. Is that okay? Was that first question?
yeah.
Second
I
question?
guess I'm just confused, like how is it equal to each other? I know you kind of,
Which two parts?
with the px squared, yeah, why is it equal to each other?
So this is just, essentially, this is just saying this y part can be moved out.
Oh, okay.
Because when I take the derivative on the y part, the derivative with respect to x on the y part, it does nothing to the y part. So the y part can move out. And so these two things are the same thing, which means up here, I can rewrite this expression with these operators on them like this, where the y part's moved out. Same thing happens when I take py, the derivative with respect to y. Derivative with respect to y does nothing to the x part, so the x part moves to the other side of the operator, and I'm just left with dealing with the derivative on the y part. Okay. Question here and then over there.
A couple questions as well. The first one, I just talked about this with Olivia, but you could use other eigen function values.
Yeah.
Right? Why
Right.
did we choose to use sign here?
So we're choosing to use sign. It's essentially just easier to write down. It's quicker to write down.
Okay.
And for the particle, in a box, it's simpler to look at. A more complete thing that we would want to look at is the combination of those imaginary exponentials, e to the ikx and e to the iky. That would be a more complete, but then you'd imagine you'd have like foiling, you'd end up with 4 terms. Still would be valid. Some cases it would actually be more useful than the sine functions, but they'd be equivalent.
Okay.
Yeah, so there's definitely other basis sets we could write it down in.
Okay, cool. And then if we wanted to just go to more dimensions, like use the z-plane, could you do the same line of thinking except just add another variable?
Yeah!
Okay, cool.
That's exactly what we do.
Okay, cool.
I'm about to write that down, but I thought I saw another question. Question back there, yeah.
The energy, is it total energy, like kinetic plus potential?
Yeah, but remember, since we're doing, I erased it just a moment ago. I shouldn't do that. Remember, since we're looking at a particle in a box, that potential is 0 inside the box.
Okay, so if you did the Hamiltonian operator on the wavefront, it would give you a different answer than this energy would give you this.
No, it would give us this energy, right? Because the Hamiltonian, so the Hamiltonian is, so this is the Hamiltonian here, right? It's the px hat squared plus the py hat squared
Okay.
with the 1/2m's. The potential energy term we said for the particle in a box is 0. For the particle in a plane, we're operating in a plane where we're in an area where there's 0 potential. We are going to do a problem, I think we'll have time for it today, of what if we do have a potential?
That was my question.
The rest of the quarter, we're going to have potentials.
Okay.
Right? We're starting without potentials, and we'll start throwing potentials at you as well. Was there another question? Yeah, question.
Why are there two separate ends?
So it turns out when we do this, right, when we solve this equation, we get some counting number associated with this equation. When we solve this equation, we get some counting number associated with this equation. But they're not the same counting number. So we need two different counting numbers. The boundary, and it's really the boundary conditions, right? There's different boundary conditions in the x dimension than the y dimension. And so we end up with, this is essentially a consequence from the x dimension boundary conditions, a consequence of the y dimension boundary conditions.
So if it was a perfect square, they'd be the same number then?
Not necessarily, right? Because you still have the functions going in different directions. We do get some simplifications. If Lx and Ly were the same length, then we could move that out and you just have n1 squared plus n2 squared. But we still have two dimensions that we have to consider those conditions in. 2 dimensions, 2 quantum numbers that we have to deal with. And that consequence is part of one of the interesting things I wanted to mention. This gives rise to the possibility of possible degenerates. Let's not actually, I just thought that would be funny. Right, we end up with possible degenerate energy levels. That is to say, if it was 1 and 1, there's only one way to get that. But it could have 1 and 2, or 2 and 1, and there's a possibility of degenerate energy where I can't, like, the energy that we measure is the same, even though the wave functions are kind of moving in different directions, or the probability densities are different. And so in those situations, we end up with this total energy looking the same for different possible n values. That's referred to as degenerate energy levels. And you've seen this if you've looked at molecular orbital diagrams or even just like atomic orbital diagrams. You got the different dashes all in the same energy line. It's because they're degenerate. And the way we fill those electrons in is slightly different. It's usually a consequence of some symmetry. You notice if Lx and Ly are different, it's really difficult to get the same energy for them. But if Lx and Ly were the same, there's a lot of options for getting degenerate energy levels, where we really can't tell which state is that energy level because there are two possible answers for that energy level. We didn't see that in the one-dimensional case. In the multi-dimensional case, we start to get these degenerate energy levels. Okay. Then, what about 3 dimensions? So if we did this for 3 dimensions, what color? Wow, I've used all of the colors. I should have brought red. If we do this for 3 dimensions, I'm just going to tuck this down over here. It's exactly what we said was mentioned before. We're just going to end up with a psi of x, y, and z equal to some x function, some y function, and some z function. And we just do the same separation. Our energy in this case, and we could write it down, it's going to be like, like a sine n pi lx x, sine n pi ly, so on and so forth. Our energy is easier to write down. We end up with a pi squared h bar squared over 2m, n1 squared over lx, plus n2 squared over ly, plus n3 squared over lz. And now we've just done particle in a cube. Right? When we're working with x, y, z, these orthogonal coordinate systems that we're pretty familiar with, the way we set up our operators was to work with this really nice using px, py, pz. So we end up with this nice separation of variables that makes it really easy to calculate or kind of see the pattern of what the energy is going to be. Now, this is like Nobel Prize stuff. If you didn't know, and what I mean by that, it is, but the Nobel Prize was given for quantum dots this year. Did you all hear about that? Some yeses, some no's. Okay, so here's the cool part. Quantum dot is a really bizarre object. It's an object, they make it out of some material, and so it's got some material properties, but it turns out that you can model it like a particle in a 3D box. And it turns out that the properties of this material of the quantum dot don't depend on the material, but the size of the object. Right? If you change your Lx, Ly, Lz, I forgot a square there, sorry. Don't forget to square those. If you change your Lx, Ly, Lz, you change the size of your quantum dot, the properties of it change not because of the material, but because of the size of the dot. Now, what they're using this for right now, or one of the things they're using it for, is by changing the size of the material, you can make the absorption and emission wavelength of the dot change. So you make the dot the right size and you can get a different color. You can get pretty much, you can get any color in the visible spectrum. Next generation monitors are probably going to use quantum dots. They're hoping they're going to use quantum dots. So instead of having RGB, you're going to have like, oh, it's like this number of quantum dots in this size range, so you can get every wavelength of light possible from your monitor. It's gonna be like, if they actually figure out how to make that technology more like durable, like next generation of screens is gonna be mind blowing. It's used for other things. It's already being used in some medical research. It's being used in imaging. It's being used in like nanodetectors, because you can make an object that essentially absorbs and emits only particular wavelengths of light. And so you can make detectors for certain emissions and things like that. It's really useful, and you can model it with everything we've done so far. Trap an electron in this quantum dot, and then it has properties from the size, not from the material. Question?
Do they synthesize the dot?
Yeah, they make these.
Okay.
Yeah, they make these. And if you remember, nanomaterials was one of those things we talked about on the first day. Whereas like quantum mechanics does great with like 1 to 50 atoms in a molecule, sometimes 100 if you're using a supercomputer to do these calculations. This was for 1 electron. Imagine if you tried to do like a carbon, something that had 6 carbons, each carbon has 6 electrons. Lots of equations. We'll look at ways to deal with that later on. So classical theory does great with things that's like 100,000 particles and more, right? When you've got like bulk material, so the wave properties kind of average out and you have some localized behavior. These nanomaterials are in this weird range where it's a material that is a particle, but it has this quantum-like property to it. And I don't know if I should say this on video, but my advisor in grad school for years made fun of nanomaterials because people were getting massive grants for it and doing all this stuff with it, and there was really nothing useful being done with it. People were like making all these materials. I'm like, whoa, we made a material. It's a nanomaterial. But they weren't doing anything with it. The only application that we could find, and we did this every year. We kind of challenged our students. It was teaching an upper division lab class with a writing assignment. Challenged our students like, hey, write about uses of nanomaterials. And like 4 quarters in a row, the only use was makeup. Because they were making this makeup that like, was really silky smooth because it was like small enough that it could fill your pores. Pros, cons, I don't know, but it was like it's biodegradable, so it was okay. But that was for like a year and a half. The only use for nanomaterials that anyone could find was makeup. And now it's like Nobel Prizes and future of electronics and all this other stuff. So, just because someone really smart makes fun of something doesn't mean it's useless. Okay. I want to give you some time to continue working on that worksheet, but I have one more really weird thing I want to talk about. It's a purely quantum mechanical phenomena that is looking at this idea of what if we do have potential. And the potential we're going to look at is particularly, what if we had a barrier in the way? What if instead of a particle in a box, with our sides going up to infinity, what if we had a particle in a well where the sides didn't go up to infinity? A little bit more realistic, a little bit more something we can imagine existing. Now, before we do the particle in a well, I'm going to do the particle on a barrier. So what this looks like on an energy map, and whenever people draw these energy maps, it took me so long to understand these things, I was always frustrated with them. So I'll also give you an example of what this might look like. Real world example. So you've got this energy scale. You've got an area of 0 energy. You've got some step up where the energy goes up and then the energy drops back down. What would this look like? This is not like running into a wall. That's the analogy that everyone makes, and it's not a great analogy. The better analogy, in my opinion, is, let's say you've got 2 wires, and there's a gap between them. So you've got a conductor where the electrons move really easily. Then you've got an air gap that acts as insulation. Takes a lot of energy to push electrons across that. And then you've got a conductor where the electrons move really easily. So we've got low energy to push the electrons around, takes more energy to push the electrons, and then drop back down to low energy. We're going to solve this problem by considering 3 regions. This region, where there's kind of just a particle moving around, the region of the step, and the region on the other side of the step. We're also going to particularly look like, so that analogy, we'll get into that analogy in a minute. This is also going to particularly look at if the energy of the particle we're going to particularly look at when the energy of the particle is lower than the barrier energy. Right? If we're higher than the energy barrier, that would break the dielectric constant, and you're just making little sparks. We could do that, right? We can crank the energy up real high and electrocute air. We've seen that happen, make little sparks. That's how spark plugs work. What if the energy is lower than the barrier? How many electrons should make it across the barrier if the energy is lower than the barrier? What does your classical intuition tell you? 0, right? 0 electrons, 0 whatever we're trying to push across should make it across. But that's not what we see on the quantum scale. So in this region 1 and region 3, we kind of end up with the same physics we've seen before. And it's region 2 where something weird starts to happen, right? So in 1 and 3, in those 2 areas, we're going to have negative h bar squared over 2m d by dx squared on psi. Right? We're going to have that typical thing that we get. This negative is going to come over. We're going to add it over, but that's the situation we get. And so in this area, and I'm going to write it down with the exponentials, even though we're not going to use the exponentials. It turns out our psi's, we're going to have a psi in region 1, which is going to be e to the, some constant we have to figure out up front, e to the I k x. That's going to be k for region 1. Plus b, e to the negative I k 1x. Psi for region 2 looks really similar. I'm skipping letters because we've got, region 3, not region 2. I'm skipping letters because I'm going to save a C and D for region 2. So I'm going to get e to the I k 3x plus f e to the minus I, k, 3x. So that's the generic function in region 1, the generic function in region 2. We've got a lot of things we still need to solve. We need to figure out that k value is going to be related to like the 2m's and the e's. The a's, b's, e's, and f's, those are all things we have to solve for. Now, the part where it gets weird, but this is just like the free particle. This is like what we did on the second day, maybe the third day. Right? But we've solved that kind of problem. We used sines and cosines when we were looking at particle in a box because we knew, well, I knew the math was going to work out easier. If we looked at region 2, this is where it gets strange. Because this class hasn't been strange yet. This is where it gets strange. In region 2, we have our first non-zero potential energy. Right? We're going to have negative h bar squared over 2m d by dx squared on side 2 plus some potential equal to the energy. We've got some non-zero, we've got a potential there now. We've got something. Now, the thing that makes it so this isn't too much more difficult is that potential is a constant, right? We're setting this up so the potential is a constant. It's not some variable thing. It doesn't depend on x, it's just a constant potential. So I can rearrange this to make it look like something over there. I can subtract this v naught over, and I can get h bar squared over 2m d by dx squared on side 2 is equal to oh, I see. Okay. The book doesn't, I've got to do something. Okay. Now we can rearrange this a little bit. This negative sign, so this E minus V naught, this is the potential bigger or smaller than our energy? And we can think about these in terms of like those two different cases. What happens if the potential energy is larger or smaller? I'm going to do a little bit of rearrangement to talk about this. I should do the same thing over here. I'll do the same thing with both places because there's a way that makes it so we can see what's going on a little bit better. Right? When we rearrange this, we get the d by dx squared on psi is equal to negative 2m e h bar squared on psi. Right? That negative sign, that was part of why we needed imaginaries, right? Because we need to take something that the derivative of something twice and get a negative value. So taking the derivative twice and getting a negative value, that said, hey, we're going to use imaginaries. Over here, if we do that rearrangement, we get d by dx squared on side 2 is equal to, and I'm going to rearrange it a little bit, 2m over h bar squared I used the negative sign to just flip the order of what was in the parentheses. So I've got V naught minus E. This, and since we're in this particular situation where E is smaller than V naught, this side always ends up being positive. So we're taking the derivative of something twice and getting a positive number. That means this is going to be real answers. Instead of having an imaginary function that's like an oscillating term, like sines and cosines, we end up with a real function. We end up with a psi 2 that's real functions. Where did I put it? Oh, there it is. See? I'm using like a script K. Oh, that looks terrible. Right? This is going to be a different thing. This whole part, we can call like script K. I want it to look different than my regular K for my imaginary part. right? So I end up with functions that are just exponential decay term. Like I've got an exponential growth term and an exponential decay term. So inside the barrier, the particle doesn't just disappear. It's got some exponential decay term and some exponential growth term associated with it. Now, we have to do a bunch of math now. Or we don't have to. We're going to skip the bunch of math. But there's a lot of math here. We have to apply a whole bunch of rules here. Right? We have to apply boundary conditions at this boundary. If this is 0 to L, we have to apply boundary conditions so psi 1 and psi 2 are equal to each other and have a smooth transition. We have to apply boundary conditions so psi 2 and psi 3 have a smooth transition and continuous. So in terms of the boundary conditions we would have to apply, I'll write them down and then I'll just write down like where this is going. We would have to have our boundary conditions would say that psi 1 of 0, right, going to that 0 part, is equal to psi 2 of 0. It would also say, to have it be smooth, we'd have to have the derivative with respect to x of psi 1 of 0 equal to the derivative with respect to x of psi 2 of 0. This one says continuous, this one says smooth, right? The slope is the same as it transitions. We'd have to do the same thing with psi 2 of L equal to psi 3 of L. And then we'd have to do the same thing with the derivative of psi 2 of L equal to the derivative psi 3 of L. We end up with these 4 boundary conditions. It makes it so this exponential growth term disappears. It makes it so this this E term disappears. There's, different things happen. And in order to make these boundary conditions, there's actually 2 others. Well, not technically. Okay, there's just those 4, right? So we've got these boundary conditions. If we apply all those boundary conditions, we get some weird things, right? We get this idea that the wave function doesn't stop existing in region 2. It exists, but with some decay associated with it. And what that means is there's some possibility, if that barrier was thin enough, there's some possibility that the particle might get to the other side before it completely decays. That idea is referred to as the transmission coefficient. Why am I blanking on the word I want to use? Yeah. Transmission probability, transmission coefficient. So let me draw a picture for what's kind of going on here. And then we'll look at this transmission coefficient to talk about what it is and how we use it. So in terms of drawing a picture, what the wave function is doing here, essentially over here, I've got to try and get this right. Over here, the wave function is oscillating. As it comes into the barrier, right, these are oscillating terms. As it hits the barrier, it becomes a decaying function, and it starts to decay. And out the other side, we get another oscillating function. You can get to the other side of the barrier. So what is, if we take a ratio of this probability versus this probability, what's that transmission amount? That's the math that we're skipping. It's this big, ugly equation that we're going to talk about. And we're going to do kind of the same conceptualization we did with that first 7a, where we're like, hey, let's just take the numbers as they go to one extreme or the other. The transmission coefficient is 1 plus e to the script kl plus minus e to the negative script kl divided by 16 e of the particle divided by the potential minus 16 times e to the particle divided by the potential squared. All the negative one, all in first. What does that mean? First off, the really cool part here, is the fact that there's any probability of being on the other side of the barrier. That's really weird, right? We all said it should be 0. It turns out it's non-zero. It's complicated, but we can look at some cases, right? We can think about physical reality and say, okay, well, what happens if the particle got really massive? So keep in mind, this k term, this script k, has mass buried in it, right? It's got the mass in it. It's 2m h bar squared v naught minus e is that k, that kappa. So as mass goes up, we can ask different things. We can ask what happens if the mass goes up? What happens if the potential barrier gets bigger? What happens if the potential barrier gets skinnier? What happens if the particle energy goes up? Right? We can ask all of these different questions. So if the mass goes up, and I had to write this down, if the mass goes up, the transmission coefficient will go towards 0. Why? That took me a little bit of figuring out to do. So if the mass goes up, e to the kl goes towards infinity, right? That k inside of there is a mass. So if mass is getting bigger, that mass, that's going to be e to a bigger number. As the mass gets really, really big, that goes to infinity. As that goes to infinity, then 1 over infinity, right? Because then this thing is equal to infinity, but then it goes to the minus 1, goes to 0. So if we get bigger particles, we see no tunneling. We need particles with really low mass to see tunneling. Another thing we can look at is what happens if the potential barrier gets really large. If the potential barrier gets really large, tunneling goes to 0. Question?
Sorry, what is tunneling again?
So tunneling, this is essentially the coefficient that tells us what percentage of the particle, like if we had like a billion particles hitting this thing, what percentage of the particles do we find on the other side of the barrier?
Okay.
And it ends up being a non-zero value.
And the box is
That's the
barrier.
potential, right? That's the barrier with some height v equals
Gotcha.
0
Yeah.
and some width L.
Okay.
I think your book actually uses W for width here, but I'm just using L. Question?
No.
Okay. So if the potential goes up, then what happens is En over V naught, these terms on bottom, they go to 0. Right? If this potential gets really large, saying it goes like all the way like massive, then this term goes to 0, this term goes to 0. And then we have 1 over 0 goes towards infinity. But it's then the inverse of that, so it ends up being just 0 goes to 0, or 1 over infinity goes to 0. So if the potential barrier gets really large, we also don't see any tunneling. Right? This is why we don't see tunneling in our day-to-day lives. Day-to-day lives, particles are massive, and the potential barriers we run into are like walls. They're really big potential barriers. We could keep going with this. We're almost out of time already. The thing that becomes interesting about this is this actually has really practical use. So this is one of those things that's purely quantum mechanical. Right? There's nothing in classical mechanics that really looks like this. People try to draw analogies of like, pretend you throw a ball at the wall and the ball just ends up on the other side of the wall. Wouldn't that freak you out? It's like, yeah, but that's not what's happening, right? Because That's a massive particle with a massive potential. You would never see that happen. But where we do see this happen is these things called tunneling electron microscopes. 1 through 5, you've heard of TEM. The tunneling part, well, a couple 5s. The tunneling part is this. So essentially what this does is if you have a surface that's on the atomic scale and you want to map that surface, you get a metal piece, you put it on a conductive material, you get another conductor, you put them really close to each other, and you run the tip across, and you measure the probability of the electron getting across. So you essentially, no sparks. If you crank the power, if you crank the voltage up too high, you spark and you just burn your material. But if you keep the voltage at the right level where it's below your barrier, you can measure a current change as this gap gets bigger and smaller, and you can measure like where there's larger objects and where there's smaller objects. And you can actually get the surface of gold, the surface of microprocessors. You can see the surface of these things. The really cool part that people have started doing, they've been doing it for years, but they're getting really good at it. They can accidentally, by changing the voltage next to certain materials, this was considered a huge problem when it was originally happening, but they're essentially dragging this across and they're accidentally picking up material, right? Single atoms like get stuck to the tip. But they've learned how to intentionally pick up single atoms and then drop them off. So they can actually use tunneling electron microscopes to build these like atomic structures, like literally atom by atom. And there's actually people who work on doing a single molecule reactivity by using tunneling microscopes to like pick up single molecules and move them around. That's not the tunneling phenomena. It's kind of it's an accident of the tunneling of people using this tunneling technology. The tunneling phenomena, like you can look up tunneling electron microscope pictures and you can see these like incredible like nanometer, micrometer scale pictures of surfaces, like resolution to single gold atoms. Like you can actually see the ridges of single gold atoms in like a gold surface. Yeah?
I think I actually heard of that. Like, I think they use that method to create the world's smallest movie, and it's called A Boy and His Atom.
I believe it. I know MIT spelled MIT out in like iron atoms. And it only took them like 30 iron atoms to do it or something like that. There's like when people first started figuring out they could do this, they were doing like, you know, the first thing they did was try to program Doom. No, I'm kidding. Nerd joke. No, but they instantly were like, I'm going to draw pictures and I'm going to do silly things. But it has a lot of like single molecule reactivity is really groundbreaking in terms of actually understanding how chemical reactions are happening. Like where that electron, like mapping to the point where you can see the electron density transferring as you create these like unstable transition states. Like it's really mind-boggling. And it's something that mostly chemists work with. This is like that's like physicists do this as well. But after you've done like enough looking at surfaces, they're like, cool, we're done. But chemists, surface chemistry, polymers, all this stuff is looking at this surface level phenomena. And we use tunneling electron microscopes to do it. It's purely quantum mechanical. It's all like relatively new technology. So it's really neat. Questions?
I could be thinking about this completely wrong, but don't like electrons and stuff have energy? Like, wouldn't there be some sort of like energy collision thing going on, like within? Like, I don't even know how that works or anything. But like, how does it just like? Isn't it just like a boundary, right? So how does like just seamlessly kind of go through?
It just does. So essentially, what happens is, so you're right. There's potential collision. There's some potential, and we can talk about that possibility of collision in terms of, well, what's the dielectric constant of that gap? And that essentially defines our V naught. Right? So we can figure out like, well, how likely is it for that electron to get across from the different setups we do? You can actually do this in open air. You can also do it in vacuum. And you know that changes your dielectric constant and gives you a lot more detail because you know current becomes like you essentially make it more difficult for it to spark, and you get now I have to think about that. But you essentially can change that dielectric constant, and you can change that possibility of like that collision idea. But in this kind of thinking about it, that would just change your V naught around, right? And you can also think, well, what else would mess that up? Well, if your tip was like really far away, that'd be like a really massive gap. The idea that you would tunnel across that with this exponential decay, just you know, as the gap gets large, your tunneling probability goes to 0. You need that tip to be really close to the surface. And then you can start to see a current, not from sparking, a current from electrons tunneling. Just popping over to the other material without existing in a classical sense, right? And a lot of the ways that we have trouble with this, right, just the idea of something colliding, is because even me, after doing this for years, my brain defaults to electrons or particles. But they're not, right? They're particles and waves. They're this quantum object that is particle and wave. Other questions? I feel like a jerk. Oh yeah, questions.
What's the biggest value T can be?
So there is, whoa, what is the biggest value T can be? I think 1, right? So there is, as the energy of the particle goes towards, as the energy of the particle goes up, there's one more we can look at. Right? If the energy of the particle goes up and up and up, there's a limit to how high it can get because we'll just start, you know, forcing the electron across, not tunneling, but just traveling across. Oh, no, I already said that. Okay, so in this situation, this is a little bit hard to write down, but you end up getting this kind of, this transmission term goes to 1. So you get like full transmission if you get the energy high enough to a limit. How this looks in a well. So this is particle. This is a particle with a barrier. If we look at particle in a well, this is where we start to get things that look more like atoms or molecules. I can never figure out which way it goes. Okay, so you end up with inside the well, if this is like 0 and this is V naught, right? Inside the well, you have an oscillating term. And then outside the well, you have a non-zero decay. So classically, you'd never see a particle exist outside of the well. Here, quantum mechanically, we're like, oh yeah, the particle has some probability of being found in what's considered a classically forbidden region. Right? You would never find the particle. If this was a ball bouncing back and forth inside of a box, the ball would never partially exist on the other side of the box. Classical analogy delusion, I know, but here, the particle has some possibility of being measured outside of this potential well. Question?
Is that because of like the boundary continuity?
Yeah. Right? Since this potential doesn't go to infinity, there's some non-zero wave function in here. One of my favorite examples for how we could think about this and make it relevant to chemistry is, where did I put that picture? This picture. So again, thinking about it, how does, I've said multiple times that you can use a particle in a box to look at a conjugated system. Right? If you looked at a chain, this is not really a particle in a box. This would be like a particle in a well. Where we've done this, if you look at this, you would have to have some kind of like, you'd have a well that kind of looks like this, right? Where the electrons, oh, I got this a little bit off, but where the nuclei are, there's some like barrier, so it's a little bit higher. Where the bonds are, there's less of a barrier. We can approximate this to be a well. Right, to try and map it a little bit easier, simplify the mathematics. We could even, if we were really not worried about the edge effects, we could just do it as an infinite well. Right? We could do it as a particle in a box if we weren't worried about edge effects. So again, this is a way where we can model simple things. If we wanted to do a two-dimensional, if we wanted to do like a benzene ring, we could do particle in a plane. If we wanted to do something like a buckyball or some large three-dimensional object, we could do a particle in a cube. Okay, sorry for going a little bit over. Thanks for being patient.